Hi everyone. Just addressing your feedback from today's lecture. I'm still a little confused about conjugate acid-base pairs. Um, Essentially, when you think about something being an acid-base pair, I think about acid-base reactions in terms of a proton transfer, either gaining a proton or losing a proton. So, a molecule might be able to donate a proton, and it also might be able to accept a proton back. If it's losing a proton, that is it behaving as an acid. The thing it becomes after it's lost its proton is its conjugate base. So this is the acid. After it loses the proton, it becomes its conjugate base. Or vice versa, if you have a base, as soon as it gains a proton, it might be willing to lose that proton again. So it becomes an acid. So this might be the base, and this is its conjugate acid. So if I was going to write that in terms of chemical equations, I might have some weak acid when it donates a proton to water, HA becomes A minus after it has donated its proton onto water and formed hydronium ions. So that's like sort of the skeletal equation for acid for a weak acid. For a weak base, a base will tend to gain protons from water, and once it's done that, it becomes, once it gains the proton, it becomes BH plus. So this B, it could be any number of things. It could be like the classic example I think of is ammonia, NH3. It gains a proton from water and becomes NH4 ammonia. So this would be the base, and this would be that base's conjugate acid. So this would be acid base conjugate acid. So a couple, one note here, conjugate acids and bases, they don't just exist in the context of a chemical equation. We think of a substance, an acid's conjugate base as what it would become after it lost its proton. So again, if you had some acid, after it loses a proton, what does it become? It becomes A minus. So if I had hydrofluoric acid, after hydrofluoric acid donates a proton or loses a proton to somewhere, it becomes F minus. We will identify F minus as the conjugate base of HF. So I got another question here. What is the best way to identify conjugate acids and bases when there are other ions present? You can sort of say, okay, if I have something like HF, so I'll rewrite this equation for HF, donating to, again, if we think of this as, we look for what changes and what doesn't change and how they change. In this reaction, this molecule loses a proton and it becomes a fluoride ion. It loses a hydrogen and becomes fluoride. If it lost a hydrogen, then it was a hydrogen donor, meaning that this is behaving as an acid. It's transferring it onto water. And what it becomes afterwards is that acid's conjugate base. So how do you identify it? It is a matter of being able to recognize what is losing protons, what is gaining protons, and what do those chemical species become after they donate protons. So there's no simple way to do it. You do need to understand, you do need to be able to keep track of or analyze and observe how hydrogens are shuffled back and forth between molecules in a reaction. Is there a way numerically to determine which solution? So this is in regard to the first problem I did between hydrochloric acid and hydrofluoric acid. The question was, is there any way to determine mathematically which one has the lower pH? Yes, there absolutely is. The way you calculate pHs is by taking the negative log of the hydronium concentration. So in any acid-base calculation where you're asked to find pH, your ultimate goal, I guess maybe not ultimate goal, your penultimate goal is to figure out what's the hydronium concentration in that solution. And that might be somewhat simple or it could be somewhat complex, and you will need to take into account, okay, what chemical reactions are occurring, what chemical species do I have in solution, what chemical reactions are occurring, are those reactions going to completion, or are they equilibrium processes where, okay, concentrations are determined by using an icebox, looking at the law of mass action? Or are they going to completion, in which case I can just use regular stoichiometric calculations where I don't have to use an equilibrium. I don't need to use the law of mass action to predict concentrations. So I'm going to do more examples. I'll work through how you do that type of analysis on Wednesday. But there is a way to calculate it. You can calculate it numerically. I'm still confused over how the sodium fluoride and hydrofluoric acid solution was acidic. Okay, let me work through that now, because that does deserve being discussed. So this was the last solution I looked at today, which was a solution of 1 molar NaF and 1 molar HF. So we take these two substances, we dissolve them in solution. What ions do we have present? Well, I'm going to have sodium ions. The sodium fluoride completely dissociates. It's an ionic compound. It will just dissociate into its constituent ions. I'll have fluoride ions, and I'll have HF molecules. The HF is a weak acid. It doesn't completely dissociate. So I will still have quite a few of those left over. Okay, so what are the important equilibria to consider? The first one here is the fact that water is going to interact with either one of these guys. You can have hydrofluoric acid reacting with water and producing hydronium and fluoride minus. Both of these guys are going to be involved in this equilibrium expression. So let's say I want to calculate the pH of this solution where I have 1 molar sodium fluoride, which essentially means I have 1 molar fluoride, and I have 1 molar hydrofluoric acid. So this is the primary equilibrium to consider. And if I want to calculate the pH, what I really want to do is calculate the hydronium concentration. So I have an equilibrium process where I know some of the concentrations and I don't know one of the other concentrations. This is something to solve using an icebox or an ice table. So I'll do my initials, my changes, and my equilibrium. I will assume that initially I have 1 molar HF, which I do. That's a reasonable assumption. I'll forget about water because it's a liquid. It doesn't factor into the equilibrium expression, into the law of mass action. Hydronium concentration, I don't know what that is. It's going to, we can safely assume it's low. If I was taking both of these and placing them in liquid water, that should only have a molar concentration for hydronium of 10 to the negative 7. Neutral water has a pH of 7, So that implies its hydronium concentration is 10 to the negative 7. That's close enough to 0, I could just say that there's nothing there. And then the fluoride ions, I should have 1 molar fluoride because I'm starting with 1 molar sodium fluoride. Okay, so that's the system that I'm starting with. It's going to shift a little bit because I don't have enough of one of my products. So I should shift and produce some products. I should shift and produce some hydronium. So this is going to go down by a little bit. This is going to go up by a little bit. And this is going to go up by a little bit. So my equilibrium concentrations are 1 minus x, x, and 1 plus x. So these are my equilibrium expressions. So let me work with that. I'll work with that over here. If I have, I know that Ka should be equal to, Ka describes this reaction where I have the hydronium concentration over the fluoride concentration over the hydrofluoric acid concentration. If I plug in my equilibrium concentrations, I get x, 1 plus x, and then 1 minus x. So HF, to complete this calculation, you do need to know, if you actually want to calculate this, I'm not going to completely calculate this, but if you were going to calculate this, you would need to know an actual value for Ka. And for HF, it's pretty small. I mean, it's not negligibly small. It happens, it does occur, or the reaction does go forward, but it doesn't go very far forward. The equilibrium constant here, I believe, is, oh goodness, did I have this in my notes somewhere? I'll give you the order of magnitude. Order of magnitude is around 10 to the negative 4. So I expect, okay, this reaction does not heavily favor the products. I am not going to shift that far forward to produce products. So I expect the amount of hydronium I produce, I expect X to be relatively small. And if it's relatively small, then I can say, okay, 1 plus X. If X is small, that's pretty much equal to 1. 1 plus something very small is still basically 1. 1 minus something small is still pretty much something, is still pretty much 1. So those 1's cancel, and then I can say, I'll bring this down here, that Ka is approximately equal to X, where X was your hydronium concentration. And since Ka is less than 10 to the negative 7, if I take the negative log of both of these, so you can take the negative log of Ka, that gets you something we call pKa. If you take the negative log of hydronium, you get the pH. So you can say that the pKa of this acid conjugate base mixture should be equal to that acid's pKa, which if you take negative log of this, that ends up being 4, which is less than 7. So it ends up being acidic. That is a very mathematical explanation of why the solution should still be acidic. The other way to think about this is to think about, okay, I have 2 substances in solution, one that behaves as an acid and one that behaves as a base. They are each in the presence of water, and they are both capable of either, well, they're not both capable, each of them is capable of affecting water. The acid can donate protons to water and make the solution acidic. The base can pull protons off of water and make the solution basic. Whichever one wins out depends on the magnitude of their equilibrium constants. HF's equilibrium constant reacting with water, that K value is around 10 to the negative 4. The K value for fluoride sticking a proton onto water, this reaction which would result in a net basic solution, the equilibrium constant for this reaction is around 10 to the negative 10. Meaning this reaction is less favorable than this reaction is. Meaning that the acidic power of HF is greater than the basic power of the fluoride, of its conjugate base. So in this mixture of sodium fluoride and hydrofluoric acid, I predict that the acidic character of the weak acid is more pressing, for lack of a better word, than the basic character of its conjugate base. So that's another argument for why it should be acidic, is that the acidic component of this mixture is more powerful than the basic component of the mixture. Or you could work through an exact numerical calculation and argue, okay, this solution, this equilibrium is such that the pH is going to end up being just equal to the negative log of the equilibrium constant for the acid. And since that equilibrium constant is less than, or rather greater than 10 to the negative 7, the pH is going to be less than 7, so it will be acidic. Going back to questions. I don't understand how to determine if a solution is acidic or basic, like in the examples today. So in all of these types of calculations, you need to spend some time just thinking what is in solution, what chemical species are there? Are they acidic species, meaning do they tend to donate protons? Are they basic species? Do they tend to accept protons? Do I have both acidic and basic components in solution? Which one is more powerful? If you have primarily acidic components, the solution is going to be acidic. If I have only HF, the solution is going to be acidic. If I have only basic components, like I only have fluoride present, fluoride is a conjugate base of HF. Or if I have only ammonia present, ammonia is a weak base. Then you know the solution is going to be basic. If you have some mixture of the two, you have to be a little bit more careful. Then you need to either use some logic and say, okay, the acidic component of the mixture is more powerful than the basic component of the mixture, it will be acidic overall. Or maybe they're not in the same concentration. Maybe one of these is considerably higher in concentration than the other, in which case they don't divide out and the concentration of hydronium is not simply equal to the equilibrium constant. That could be a little bit more tricky, and then your analysis becomes a little bit more tricky. But that's the general way you approach it, is you need to think about, okay, what is in solution? Are they acidic components? Are they basic components? And we will get more practice with that, numerically speaking, in just a bit. What does base dissociation mean? Yeah, base dissociation, it sounds awkward, but base dissociation is basically, I need to find up a different adverb. Base dissociation describes this process. This is also another reason why I don't like the term dissociation. I will just say acidic action versus basic action. Acidic action is donating a proton. Ka describes something acting like an acid to water. So it's implicit that you're acting as an acid to water. That is this expression, or rather this Ka refers to this type of chemical equation where I have a reactant acting as an acid towards water, donating a proton onto water. Base dissociation is the exact opposite process in terms of a substance taking a proton, acting as a base towards water, taking a proton from water. So that would be this reaction as written. This is showing fluoride acting as a base towards water. meaning that a proton is transferred from water onto fluoride. So that's what I mean when I say base dissociation. How is, so I got a couple of questions about this. How is the sodium fluoride solution, so not this one that I already did, just the sodium fluoride solution. How is that solution basic? Didn't we neutralize HF with sodium hydroxide? Didn't we produce this salt from the neutralization of hydrofluoric acid and sodium hydroxide? Yes, we did. And here's where I will admit a possible confusion, which is the word neutralize is maybe not the best word to use. Or that we have two ways of thinking. We can think of neutralization as a type of reaction where a base reacts with an acid. We can call that neutralization. And that's what I mean when I said, that is what I meant when I said HF is neutralized by sodium hydroxide. Let me actually write that out. HF. It is neutralized in the sense that, okay, I have an acid, it reacts with a base, and the base completely reacts with the acid. So this reaction goes to completion because the hydroxide ion is a very strongly basic reactant. It will very, very strongly take protons from hydrofluoric acid. Because it completely takes them, this reaction goes to completion, so you get sodium fluoride plus water. So I would call that neutralization in the sense that the reaction goes to completion, in the sense that the acid reacts with the base. And again, we originally discussed bases in terms of their ability to react with and neutralize acids, to diminish their acidic character. Then there's a different way to conceptualize neutralized. If we think of, okay, a pH of 7, that's what we call neutral, which means that you have an equal concentration of hydroxide ions and hydronium ions in solution. That the autoionization equilibrium for water is in perfect balance, just as much acidic character as basic character. That's a different way to conceptualize neutral. So your question, didn't we neutralize the HF with sodium hydroxide? Yes, we did. We reacted these two species together and we reacted away the HF. In that sense, the solution was neutralized. It is not neutralized in the sense that after the reaction goes to completion, there are still acidic and basic components to that solution. So the water is not acidic or, well, I guess I take it back. Water is amphoteric and it can behave as either an acid or a base, but I wouldn't say that it is very acidic or very basic. The sodium ion's not going to do anything, but the fluoride ion is basic. The fluoride ion has a finite base dissociation constant. It will react with other water molecules and reproduce a little bit of HF and, more importantly, produce some hydroxide ions again. So this is sort of like, this might be the primary reaction, meaning it happens first, it goes to completion. This is a secondary after the is a secondary reaction that occurs in the solution and reaches equilibrium after the first acid-base reaction, the acid-base neutralization reaction, has taken place. So in that sense, that is the explanation for why the sodium fluoride solution is basic, is that fluoride is the conjugate base of hydrofluoric acid. It is capable and very willing to take protons and reproduce HF. how can you tell if acids and bases are strong or weak? Do you just need to memorize them? Essentially, yeah. I will go ahead and say, here's what I would say. You should memorize the strong acids, and you should memorize the strong bases. The strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, chloric acid a little bit, and that's about it. There's really not that many strong acids, and similarly, there's not that many strong bases. The strong bases are all of the metal alkali metal hydroxides, sodium hydroxide, lithium hydroxide, potassium hydroxide. Those are all strong bases. There are other stronger bases than that. Sodium hydride is quite basic in solution, but those are ones I wouldn't expect anybody to memorize. Other than just memorizing them, you can assume that if I give you an equilibrium constant, if I give you an acid and if I give you a problem, and the problem has an acid in it, and as part of the problem you are also given the Ka of that acid, you're given the acid dissociation constant. If you're given that, you can assume it's a weak acid. If something is described by a Ka, that means that it is a weak acid. Weak acids meaning that this reaction between the acid and water does not go to completion. It does not completely dissociate. It doesn't always, 100% of the time, transfer a proton onto water. That occasionally goes backwards. It takes the proton back from water. That means it's an equilibrium process. That means it's a weak acid. Strong acids are ones where this equilibrium is so far to the right. So far to the right, you basically assume it goes to completion, in which case you are not going to be given an equilibrium constant for it. I mean, I will never use the equilibrium constant of a strong acid in any calculation. I've never done that. You can calculate it, I guess, but you'll never use it. So you can kind of contextually tell whether something's a weak acid or a weak acid or a weak base. If you're given a Ka or you're given a Kb, you can pretty safely assume it's a weak acid or a weak base. And other than that, yeah, I would say just learn the strong acids, memorize them. That's something that people will basically expect you to do anyway. After you've taken a chemistry course, is that you should at least have some knowledge of the strong acids and bases. Is every product of an acid-base neutralization reaction basic, or is that just sodium fluoride? I won't say it's just sodium fluoride. I will say it depends. If you react a strong acid and a strong base, the product of that reaction should be neutral. So let me give you an example. Consider these two strong acids, HCl, which again I am writing as going to completion, not an equilibrium reaction, and sodium hydroxide going to, I will emphasize here, again, these are going to completion. They do not go backwards, meaning that sodium has no desire to gain hydroxides and go back to sodium hydroxide. It has no desire to gain protons or lose protons. I mean, it doesn't have any protons to donate, but it has no desire to gain or lose hydrogens. Chloride, similarly, does not tend to gain protons back. This backwards reaction essentially does not occur. So chloride is not an acidic compound. It's not a basic compound. It's the conjugate base of HCl, but it is an exceptionally poor base. Poor in the sense that, again, this backwards reaction just doesn't occur. So when I mix sodium hydroxide and hydrochloric acid, what occurs here is the proton is transferred onto the hydroxide group, and I'm left with a chloride ion and a sodium ion. So I have sodium plus, chloride minus, and H2O liquid. That solution will be basic. So again, this is a reaction between a strong acid and a, that's a base. And a strong base. A strong acid. Strong base, strong acid. There we go. Strong acid, strong bases, when they react together, you get a neutral solution. Again, because the products themselves are not acidic or basic. Neither one of them, they are the conjugate acids and bases of something else, but they're the conjugate acids and bases of strong acids and strong bases, and those go to completion. They don't go backwards. If I were to say react a strong base, you know what, I'll do something different. If I were to do a weak base, and a strong acid. So I'm going to donate a proton onto ammonia. That will become NH4 plus and chloride minus in solution. And this solution will be acidic. So I have a weak acid and a weak base and a strong acid. And I almost hesitate to say this. When I first learned this, I tried to rationalize it to myself like this, which is, well, I'm adding a weak base and a strong acid. The products are acidic because the acid is stronger. That is not the explanation for why the products are acidic. That was how I first tried to explain it to myself, and I recognize now that is not correct. The real reason, I mean, you can use that to remember, but that's not an explanation. That is not the correct explanation of why the solution is acidic. The reason why the solution is acidic is because the products of this neutralization reaction, one of them is a weak acid. NH4 is the conjugate acid of ammonia. When NH3 reacts as a base with water, it produces NH4 plus and hydroxides. And again, NH3 is a weak base. That implies that the reaction doesn't go to completion, it occasionally goes backwards, meaning that ammonia occasionally donates protons to something else. So ammonium, the NH4 ion, is an acidic compound, or it's an acidic ion. So if you have it in solution, that solution will be slightly acidic. That is the explanation of why the products of this neutralization reaction are not actually neutral. So I hope that further explains or clarifies your question. Does shifting reactions left or right only apply to equilibrium reactions? Yeah, I will say that concept of an equilibrium of a system shifting left, shifting right, really you should only use that word in reference to equilibrium systems. Case in point, we didn't talk about that. We didn't use that language until we got to equilibrium reactions and Le Chatelier's principle. So it would be unreasonable if it were at play for earlier reactions, for non-equilibrium reactions, we might have introduced that language. But we waited until we got to equilibrium reactions. So it only applies to equilibrium systems. Following that, I had another question. What does it mean for a reaction to shift left or shift right? Shifting left versus shifting right. Shift meaning how do concentrations change? If an equilibrium system shifts to the left, shifting to the left means produce more products. So if you shift, I'm sorry, not shifting left. Let's say I shift right. I've already gotten this. I've already started. If you shift right, that means produce more products, meaning their concentration should increase. The equilibrium concentrations adjust, and you end up with a higher concentration of, this is not an equilibrium reaction, I'm just using it as an example, but you would produce more products, their concentrations should go up. We say the reaction has shifted in that way. Conversely, if it shifted to the left, that would mean that you produce more reactants. You end up with a higher concentration of sodium hydroxide and HCl. Again, not an equilibrium reaction, I'm just using it as an example. Is it possible to tell that a Ka is less than 1 without the info being given? So can you ever just look at a chemical and decide its Ka must be less than 1? Not easily. You can make a prediction about how stable something will be or how readily it will give up a proton. But that takes a pretty good understanding of molecular structure, chemical bonding, and thermodynamics a little bit to sort of rationalize how those are all put together. And I would argue we're not there yet. I know everybody has learned some chemical structure, and I can show you a Lewis structure and you can tell me whether it's a viable Lewis structure or not. But people, I'm gonna guess, are not going to be as comfortable deciding whether something is a higher energy state or a lower energy state. That's a little bit trickier, or rather a higher energy molecular structure versus a low energy molecular structure. That's a little tougher, and we will try getting to that maybe later this semester. Definitely by the time you get to organic chemistry, you'll start discussing that much more. Usually that analysis doesn't get brought up in general chemistry. So I will say that for the moment, you can't easily predict whether something has a large Ka or a small Ka just by looking at it, but you can use some intuition. If you know something is a strong acid, or if you know something is a strong base, then you can say that its Ka is very large, or that its Kb is very large. Because again, for both of those, Ka and Kb, they're just equilibrium constants. They favor the products. So in that case, that means the reaction goes to completion. And that's what we mean when we say something is a strong acid. It dissociates a proton. It transfers a proton and doesn't take it back. That reaction goes to completion. Ka is very large. So if you know that something's a strong acid, then you can say that Ka is large. If you know that it's a weak acid, you can say Ka is small. And the same way for bases. If you know something is a weak base, then you can say that Kb is small. But other than that, it's not really easy to predict that with no other knowledge. So I'll say that for the moment you can't easily predict it, although you can occasionally infer that it should be large or small. What's the difference between K, Kw, Ka, Kb, all these equilibrium constants? So let me just write those out. So K is just referring to any possible chemical reaction, any equilibrium. That is the equilibrium reaction. Any equilibrium reaction, you can write an equilibrium constant, or rather you can write a law of mass action for it, and the law of mass action tells you that that reaction quotient should be equal to K at equilibrium. Kw is an equilibrium constant. It describes a reaction with a law of mass action. It is for a very specific reaction. K is just general, very, very general. Any equilibrium reaction has a K. This Kw refers to a specific reaction, which is the autoionization of water. It's specifically referring to this reaction. So again, you can write an equilibrium expression for this. You can write the law of mass action. You'll get products times each other divided by reactants. They're not in the reactant. They're not in the law of mass action because they're both liquids. So you get that Kw is concentration of hydronium times the concentration of hydroxide. That one's important simply because that autoionization process is always occurring in water. So we will use that to make further inferences about hydroxide concentration versus hydronium concentration. Ka and Kb describes yet another equilibrium process, another equilibrium reaction. It is specifically referring to an equilibrium reaction where you donate a proton to water. So the example I normally use is just like if you have some generic acid, you react it with water and you get H3O plus A minus. This, if I were to write this reaction shows something acting as an acid towards water, and how readily does that reaction go forward. That is going to describe the acidic character of this chemical species, whatever it is. Kb is similar. It is also describing another equilibrium reaction, but it's specifically one where you accept or you take a proton from water. So I might have some base reacting with water and giving me BH plus OH minus. That reaction shows some unknown base behaving as a base, taking a proton from water. And I can write an equilibrium constant for that, a law of mass action for that, just like I can any equilibrium. And I will give it the special subscript B just to emphasize this is describing how a particular substance behaves as a base towards water. Can you please post the, alright, so these last two are just sort of administrative things. Can you please post homework assignments as Word documents and not PDFs, or could you post both? I had originally been posting Word documents. Yeah, your comment, which I think is valid, is that it's easier to type on the document file if it's a Word document as opposed to a PDF. I will start posting both of them. I had been originally posting Word documents because I write up the homework assignments in Words and I just post them, and then I realized I use Microsoft Equation Editor to like build in all my chemical equations, and I use it for my solutions, and the Brightspace website doesn't handle those very well, and it looks like crap. And so people were having problems like reading the homework assignment. So I had switched to PDF just because it was a little easier for the Brightspace website to handle. So I'll start posting both of them. Hopefully that won't be. It's been my experience. The more things you do, the more things are prone to mistakes. So hopefully that won't cause more mistakes, but I'll start posting both of them, and hopefully it doesn't cause added confusion for people. About today, everything was answered, or I was satisfied with everything, but it would be helpful if we got some more example problems to solve for practice. You will definitely get those. I will either be giving them in the form of homework, I might have another quiz here and there, but you will definitely get more example problems. I'm going to do some example problems in class on Wednesday for calculating pHs of acid-base reactions, and so on and so forth. But don't worry, rest assured, you'll get lots of practice on this. Okay, so that is all of the questions for today, all the feedback for today. I will see everybody on Wednesday.